stability of an alternator. Let's start by drawing the phasor diagram. Let's ignore the resistance, therefore that will be IA, and perpendicular to that we will have IA XS. That will be the induced EMF. Load angle, power factor angle. Now if we draw a line perpendicular to IAXS, that will be our 1 per unit power line. Now by either changing the excitation, if we make it either bigger or smaller, E changes, and if we change delta, P changes. Now let's say we increase E by 10%, then it will be that long, and now it will move on this line 1 per unit until it reaches that operating point. Delta now has become smaller, and our current has changed like that. If we now decrease E, so that E now becomes 0.9 E. E will become shorter, and now it will move up until it reaches the 1 per unit line, and we will have the operating point E2 there. Now delta has increased, and the current has changed as well to a leading power factor. Now if we look at this, this is our unity power factor line. To this side it is lagging power factor, and to that side it's a leading power factor. If we now increase our output power, that was 1 per unit, let's say we increase it by 10%, then that will be our new power, 1.1 per unit. Now E will follow that route until it reaches that point there on 1.1 per unit, and therefore that will be our new load angle, and the current will have become leading. Now let's just have a look at an example. These problems will always be solved to scale. So you must choose a appropriate scale, and then start the problem. So the first step will be to calculate our induced EMF. If we look at the exercise 2.4 number 1, where we have a 6 kilovolt 3-phase 50 Hz star connected alternator with a synchronous impedance of 0.6 plus J10, and it supplies 100 amp at unity power factor. Therefore, you can calculate the induced EMF per phase which is 6000 divided by square root 3 angle 0 plus 100 0 angle 0.6 plus J10. That gives us a value. Now we are going to draw this to scale. So you choose a certain scale for your voltage so that it's not too small, well, almost half a page to a full page. So therefore, there we start. That is V. Our current is unity power factor, and that will be IAZS. That is E, and again our 1 per unit line. Now, with the aid of a load diagram, determine the armature current and power factor at which the machine will operate if the power input is increased by 100% while the excitation remains constant. Now that means that our power will have doubled and the new power line will lie there. With E constant, it will rotate until it reaches that point on the graph there. So that is our new load angle. Let's say that is E1. And now our power factor angle will be measured there. Power factor angle, measure the angle between E1 and IAZS. Okay. Now measure E1 E1V to scale. We divide by Z, and that gives us the current. Now the second part of the question is determine the armature current and power factor if the power remains at 200% and the excitation is increased by 1.2 per unit. So now, as E becomes longer, it will move downwards until such point that it touches the line 2 per unit, and therefore that is the case. Let's say that is E2. again measure the angle between E2 and IAZS. That'll give us the power factor angle. Also measure E2V to scale. Divide by ZS, and that'll give us the current. Now for question 3, we must determine the maximum power output. Now remember, for maximum power output, our load angle must be equal to our impedance angle. And therefore, if we butcher this picture a little bit more, this angle here is where delta is equal to beta. And then for the same current here, that is now, let's say, E3. And to get our values, do the same as in the previous steps. Thank you.